All right, on to our next example. So we're going to sketch this next function here, y equals x to the 5/3 power minus 5x to the 2/3 power. And once again, we want to do the same thing that we did before, go through all of those 7 categories and look for the characteristics that'll be useful when trying to graph our function. So this guy is defined everywhere. These two power functions both have positive exponents, and so we can plug in positive numbers, negative numbers, 0. Everything is allowed. So the set of all real numbers, remember that's the notation for the set of all real numbers. That one was pretty easy. Let's look at intercepts. Starting with the x-intercept, remember, plug a 0 in for y, so I have to say 0 equals x to the 5/3 minus 5x to the 2/3. I want to solve this by factoring, so I'm going to factor in x to the 2/3 out. This is equal to x to the 2/3 times, this would leave behind just an x, minus 5. So that gives me 2 intercepts, one occurring at x equals 0, the other occurring at x equals 5. So those intercepts would be the origin and 5, 0. I have 2 points that I could put on my graph. Y-intercepts. Here we would plug a 0 in for x, but then that would just give me y equals 0, which we actually already knew, because if we have the origin on our graph, that's on the y-axis, so that must be the y-intercept. And remember, you can only have at most one y-intercept for a graph. So I'm not going to restate that. I already have that as a point listed here. The next thing was symmetry. And remember, this function is not periodic. You're going to know that it's periodic generally because it's going to involve trig. There's other ways of defining periodic functions, but for the most part, that's what you're looking for. This function will not have even or odd symmetry. And again, it's easy enough to verify by plugging negative x into this function and then seeing what happens. But I'm not going to do that. We're just going to skip past the symmetry part since this doesn't have any symmetry. Asymptotes. Does this thing have any asymptotes? Well, it can't have any vertical asymptotes because its domain is the set of all real numbers. And remember, if its domain is a set of all real numbers, that means it has no not just discontinuities, it has no places where it's not defined, and you need that for a vertical asymptote. So definitely no vertical asymptotes, and no horizontal asymptotes either, because if I let x approach infinity, these two guys, well, actually, let's do this. I shouldn't just talk this through. I should be writing some stuff down. So vertical asymptotes, we decided there was none. Okay, for horizontal, let's look at the function and see what happens. So remember, we've factored this function up here, and if I were to write it in the factored form, 2/3 times x minus 5, then if I let x go to infinity, then both of these factors are becoming larger and larger positive numbers. These are both approaching infinity. So a very large positive number times a very large positive number, it's going to infinity. And it's also, what's happening is as x goes to negative infinity. Well, this, because of the 2 in the numerator here, will always be positive. And if I plug in, numbers that are further and further in the negative direction here, this becomes a very large in absolute value negative number. So I have a very large positive number multiplied by a very large in absolute value negative number. I get a very large in absolute value negative number. So this is going to negative infinity as x goes to negative infinity. The fact that neither of these are approaching finite numbers is what tells me there's no horizontal asymptotes. So I could also say none, no horizontal asymptotes. Okay, after asymptotes, we start using calculus. So we're looking at the increasing, decreasing test here. increasing, decreasing. All right, so I need to look at my derivative, y prime. The derivative here would be 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Power rule again, pretty straightforward. Remember, we want to look for critical numbers. Where is this thing equal to 0 or not defined at all? If I set it equal to 0, I can factor, so I can take a 5/3 x to the negative 1/3 out of that, which would leave me with x minus 2. That's what we left there. Okay, now looking at this thing, this has two critical numbers. It's only equal to 0 when x is equal to 2. Because if you look at this factor, you can't plug 0 into that, because that's a negative exponent. That's the equivalent to dividing by 0. However, that tells me that 0 is also a critical number because it's where our function is not differentiable. So when I'm doing my increasing decreasing test, I need to use both 0 and 2. Okay? Now, if we move to the left of 0, and again, I'm going to just kind of state the results here, let you plug in numbers. Pick a number to the left of 0, that would be any negative number, and plug it into your derivative. What's happening? Well, you'll see there that you get something positive. It's increasing to the left of 0. Take a number between 0 and 2. 1 is the obvious choice there. Plug a 1 in, I get 5/3 minus 10/3, which is negative 5/3. I get something negative. Should be a prime there. F prime of x is negative here. What about if I pick a number to the right of 2, say 1 billion, something really big, you know? Then what I'm going to get is a very large number here minus a very large positive number here minus a very large or very small positive number here. Small because that x is going to go down into the numerator because of that negative exponent. So that's going to give me something positive. F prime of x is positive there. Okay, so we have increasing and then decreasing and then increasing. Summarizing that, we're increasing on the intervals negative infinity to 0 and 2 to infinity. We are decreasing on the interval 0 to 2. Okay? Next up, local max and min values. Okay, remember both of these are critical numbers. It's just the reason why they're critical numbers that changes in one or the other. So what's happening here? We're increasing, we get to 0, and then we decrease. Not only that, 0 is a place where this function is not defined. So I'm expecting a corner, or sorry, the function's defined, but the derivative is not. So I'm expecting a corner or a cusp because our function is not differentiable. We might get something like this. Increasing, decreasing, okay? Here we go from decreasing to increasing. So I'm expecting, and this is where our derivative is equal to 0. So something more like that. Okay, I'm expecting that kind of behavior. I also need to plug these numbers in. So I need to plug 0 into the original function, which is easy enough to see would be 0. We already knew that, right? Because we found that 0, 0 is a point on our curve. So I have a local maximum of 0 at x equals 0. I also have a local minimum, which occurs at x equals 2. If we plug that into our function, we get, I'm going to give a decimal approximation for this one because what we're dealing with are a lot of cube roots and stuff like that because these are rational exponents. Plugging 2 in does not give me something pretty. Rather than leave things in terms of radicals, I'm going to use decimals so that it's easier to identify where this point is on the graph. The local min here is going to occur at negative, of negative 4.762. That's an approximation at x equals 2. And again, if you're wondering where that number came from, you would plug our critical number 2 into your original function, and you get something that's approximately this, okay? So that gives us a local max and a local min. Next up is concavity and points of inflection. So concavity and points of inflection. So once again, we need a derivative, second derivative in particular. So y double prime is equal to, I'll just do that really quick, 10/9 x to the negative 1/3 power plus 10/9 x to the negative 4/3 power. Okay, let's set that equal to 0 because that's how we find points of inflection. Factor out 10/9 x to the negative 4/3. That's going to leave me with x plus 1 right there equals 0. I'm not going to get anything from this because this is not defined at 0. So you might be tempted to look at that and think that 0 is a solution, but we already know that this entire function is not defined, or the first derivative is not defined at 0, so the second derivative can't be either. But x equals negative 1 is the one and only solution to this thing. So I might have a point of inflection there. Okay, so again, what we want to do is check for concavity on either side of negative 1. So you pick a number to the left of negative 1. Let's just say negative 10 or something like that. Plug it in to a calculator, see what you get. In this case, what we're going to see is that it's negative. Our second derivative is negative there. And then if we do the same thing here, f double prime of x, plug in a number to the right of negative 1, and even though 0 is not a point of inflection because it's not the second derivative is not defined there, it is a place. Actually, I'm sorry, no, let me back that up. I'm not going to include that because we know that the function, I was treating it like a vertical asymptote, which this is not. F double prime of x, if you plug in, say, 0 into this, into your, oh no, I'm sorry, you can't plug 0 in. Plug in like a 1. Then you have 10/9 plus 10/9, which is positive, so we get concave up there. So this is concave up on the interval negative 1 to infinity, concave down on negative infinity to negative 1. I think I forgot to write this part in my last example. And because concavity changes, we have a point of inflection at the point negative 1, and then you need to plug negative 1 into your original function up here to get the y coordinate of that point of inflection. It comes out to negative 6 when you do that. Okay, let's try and put all of this information together now. Once again, this function is defined everywhere. Its domain is the set of all real numbers. We have x-intercepts at the origin and at 5, 0. So if you notice with my last graph, I'm only labeling the parts of my axes that are actually points of interest. So the origin, and then I'm just going to say 5 and put an x-intercept right there. I'm not going to put any other labels because I don't really need them yet, anyways. We determined that there was no asymptote, so I don't need to worry about that. Increasing and decreasing, and local max and min. Let's take these together. So we determined that we have a local maximum at 0, 0, right? And that would be here. So if 0, 0 is a local maximum, that means that in at least a small interval surrounding it, the function must be below the x-axis there. We also determined that it's probably a corner or a cusp. But notice concavity plays a role there, so we should check our results in this concavity section with the shape that we kind of guessed our function would take here. Remember, our function is concave down to the left. Oh, I'm sorry. It's concave. I'm in the wrong place. It's concave up near 0. That's kind of what we determined here. If 0 is here, we saw that it's concave up just to the left of 0, just to the right of 0. So this is concave up on both sides, the way that I sketched that. I am expecting my graph to do something like this. Okay? Let's see, what else do we know? I think I made it a little too shallow. I'm going to have to fix that. But anyways, what else do we know? We know that we are decreasing from 0 to 2. So let's put 2 right here. And we also know that we have a local minimum of negative 4.762 when x is equal to 2. So I'm going to fix my graph a little bit, but let's put that maybe here, negative 4.762. So I should have a point like right there. So I'm expecting this thing to do something like this. It's concave up, which I'm not showing that well, but it is concave up there, which this is telling us right here. And we also have a local minimum here, so it should come back up. And we know that we have an x-intercept at x equals 5, so it's going to pass through there. It's going to do something like that. Okay? Does not look very good. So that kind of takes care of the right side of the graph. Let's look at the left side now. What points of interest do we have over there? Well, we know that we're concave up on -1 infinity, concave down on negative infinity to -1. And that -1 is giving us a point of inflection. So -1 would be here, -6 would be here. We should have a point like right about there. So I definitely made that too shallow. It should do something more like this. Okay, now it's concave up on this side of -1, but it switches to concave down to the left of -1. So it should do something like that. Okay, it's a little subtle, but you can kind of see how it changes from concave up to being concave down there. I keep sketching this graph when I'm off camera. I have to stop doing that. Okay, so this, even though it's a little messy and I have this kind of messed up portion right here, this is roughly what the graph is going to look like. Obviously, I can go to a graphing calculator, Desmos or something, plug that in, and just verify that it looks right. Okay, which I already did, so I know that's good. All right, I think I'm going to do this one on the next video. So let's go ahead and stop this here.